Hello! Today I'd like to talk to you about my research on collagen. Versions of collagen can be found in nearly every part of our bodies, as it is the most abundant protein found in all animals. In fact, about 30 to 40% of protein found in the human body is collagen. Defects can cause a range of conditions with a large variation in degree of severity, including Marfan syndrome, lupus, rheumatoid arthritis, and more. I first became interested in the role of collagen in the body after I was diagnosed with type 3 Ehlers-Danlos syndrome, or EDS. EDS is a connective tissue disorder that can affect essentially every organ system and cause symptoms including hypermobility, food sensitivities, and chronic pain. Because collagen is the general structural component of connective tissue, my personal research naturally led in this direction. I hope you enjoy learning about this protein as much as I did. By now, you're probably curious to know a little more about this protein structure, as well as its actual purpose in the body. Collagen is classified by the protein database as a structural protein. As the principal tensile element of tendons, cartilage, bones, and skin, it essentially prevents the human body from falling apart. It's also necessary for a large variety of functions, including tissue scaffolding, tissue morphogenesis, tissue repair, and more. This protein has 3 coiled subunits that form a triple helical structure as shown. This structure is important to collagen's function because it gives collagen the rigidity and strength necessary to provide support. In order for the triple helix to form, a glycine must be present at every third amino acid, or else the molecule will be poorly formed and unstable. The molecules pack together as long, thin fibrils that link to each other or to other matrix components. There are 16 different types of collagen, but the majority of the collagen found in the human body are types 1, 2, and 3. Type 1, which is found in bone, is the most prevalent, and mutations can lead to brittle bone disease. Severe mutations can also result in death before birth. In my research, I noticed that many organizations are currently researching collagen, especially for cosmetic purposes. If you've ever been in a skincare or makeup aisle, this probably doesn't come as much of a surprise. For the purposes of my research, however, I attempted to narrow down my search to collagen and connective tissue. Many facilities and institutions are currently researching this topic, including the Center for Medical Genetics, the University of Exeter, the School of Life Science, and the Craniofacial and Skeletal Diseases Branch National Institute of Dental and Craniofacial Research. The last group was a significant contributor to one of my favorite papers that I read while researching collagen. The study conducted tests to see if mice who were deficient in the gene MT1-MMP would develop diseases due to inadequate collagen turnover, including connective tissue disorders. One of the major experimental techniques in this experiment was the southern blot, which is used to detect a specific DNA sequence in a DNA sample. The experiment is performed using the transfer of electrophoresis-separated DNA fragments to a filter membrane, combined with a fragment detection with probe hybridization or a radioactively labeled DNA fragment. The image shown provides the results of the southern blot test. As you can see, there are 3 types of mice: wild type, heterozygous, and homozygous mutant. The plus sign in this case indicates the dominant trait of being mutation-free, whereas the minus sign represents the presence of a mutation. The wild-type mice acts as the control for this experiment because they do not possess the deformity. Fragments of mouse DNA were hybridized to the P5' probe, meaning that both the altered and unaltered genetic material moved towards the P5' probe. This indicated the length of genetic material, and therefore indicated the types of mice. The mice with the deformity were expected to show shorter lengths on the southern blot because part of the DNA was cut to produce the MT1-MMP deficiency. The 4 length markers were 4.4, 6.6, 9.4, and 23.1. The short DNA, indicating mutations, was found closer to the 4.4 marker. The long DNA, indicating normal mouse DNA, was closer to the 6.6 marker. Homozygous mutant mice showed DNA only near the 4.4 marker. Heterozygous mice showed DNA at both the 4.4 and 6.6 markers. Homozygous wild-type mice without any mutation had DNA at the 6.6 marker. This was important for the conclusion so that the experimenters could determine which mice possessed the mutation so that it could then be observed how the deficiency affected the mice. For example, it was shown that the heterozygous mice showed no difference from the wild type, whereas the homozygous mutant mice experienced several deformities, such as growth impairments, hyperkyphosis, and arthritis. One of the biggest complications while researching collagen for me was finding studies specific to their role in connective tissue disorders and other diseases. I learned rather quickly that the research either hasn't been done or it just isn't available yet when it comes to connective tissue disorders. If I had the chance to decide what the next step would be in the study of collagen, it would be studies specific to connective tissue disorders and precisely how collagen structure and function are affected in these cases. In order to do this, I would use X-ray diffraction to determine the structures of collagen in both healthy individuals and those with connective tissue disorders, in order to see the similarities and differences in structure. In order to determine function, I would like to see the study discussed previously expanded upon. Perhaps glycine could be removed from different locations on the collagen molecule to see what effect this would have on the rat's quality of life and expectancy.